All right, as part of our first two modules, I'd like to give some mathematical and statistical background. This comes out of chapter one of your book, and it's important information. This should be familiar to anyone who's taken college algebra or higher, uh, although I do strongly recommend for this course more statistics than most FIU biology students have had by their junior year. Statistics is absolutely critical to modern biology, and you can't participate in it without it. We should make you take statistics before we let you into a biology course. I digress. All right, so population genetics is in part about molecular genetic variation, but it's also about phenotypic variation, variation or quantitative variation in organisms that we can measure with numbers. And that may be color. We can quantify color. It may be shape, size, pattern, such as variation in these snails, featured on the textbook cover and throughout the book. Population genetics is a unique field, and as part of this first module, I want to sort of re-emphasize that population genetics is empirical, measures variation in populations. It's experimental. We can perform experiments that manipulate forces that we think should affect patterns of variation in populations and measure their effect. And it has a rich theoretical background, much of which actually predates the empirical and experimental work. But all three go together, and we can't teach or practice this field without some combination of all of them. Key to this is being able to measure phenotypes. Phenotypes in a population, they vary, and that means we're going to measure them in many individuals, and among other things, we're going to want to calculate a mean. For many phenotypic traits, such as height in humans, there's a mean and there's a distribution around it that's equally distributed on both sides. So this is a standard bell curve or normal distribution, where 68% of the variation is within one standard deviation, and within 95% of the variation too. So this is an important concept. Not all variation follows this. Some variation is binomial. Some follows a Poisson distribution, or other distributions that have a different characteristic, where most of the variation, for example, would fall here with a big fall off. Some variation follows a uniform distribution that's spread evenly across trait space. But a very common distribution is this one, the normal distribution. We can use a standard deviation to measure how far away from the mean a point is, or how widely spread the data is around this mean in the distribution. The variance, an important concept you have likely been taught and forgotten, is the square of the standard deviation. Standard deviations are the square root of the variance so that it's in the same units. The variance is essentially calculated by determining how far each point that you've measured is away from the mean. And we square each of those distances so that the distance in both lower and higher from the mean weighs equally. So the variance is not in the same units, it's in squared units. But both the variance is a concept that we're going to come to repeatedly. It's also worth taking a moment to review how we read graphs. Unfortunately, this is something we have to do. The proportion is the amount, is basically the number of measurements. This is our y-axis. And the x-axis is the value of traits. This x bar, to review notation, means the average or mean. And you're going to see that a lot throughout this course. Right, so we've known for well over a century that many traits follow this pattern. This is a normal distribution of height of individuals. In many American populations, this, particularly of men, this distribution would now be quite a bit higher. All right, so we can look at this distribution that gave rise to the figure before. This is the underlying data and the number of people who have a particular height in inches. And this is their deviation from the mean. And you see the square here indicating how far they are from the mean. And this one very short individual, it flies farthest away from the mean. All right, so one thing that population geneticists can often do, particularly in short-lived organisms, is look at frequency over time. So here the x-axis is time throughout the years, and we're looking at the frequency of F at different sites, colored different ways. And you're going to see a lot of graphs like this. It's important to remember frequency or proportion, ratio, indicate that it's a value out of basically 100% or out of 1 in the case of a frequency. All right, so if something has a frequency of 1, it means it's the only thing there. And this suggests that this is a polymorphic or segregating population where not everything is big F. Another frequency graph, this is of melanic pepper moths at different distances. And you see that these frequencies differ. Here, nearly all of the moths, close to 1, 90% frequency, are melanic. This other site, they are not. We will also look at pedigrees this semester. So F1 are the immediate offspring of a cross, a single mated female fly. And in F1s, if the parents are heterozygous, you're going to get 50-50 proportions in that F1. In the F2, they're going to segregate, and the proportion may vary in F2 lines after that, particularly if you take different offspring from that F1 and separate them. So we can look at lots of different kinds of data in this way, such as lethal or semi-lethal chromosomes in fruit flies. And we can compare what we observe to what we expect in different populations. And this is something that we'll come back to in the next module in Hardy-Weinberg equilibrium. Another thing that we're going to look at is frequency versus fitness, in this case relative viability. And we may compare homozygotes and heterozygotes. This is another prompt to you to review terminology like this. In some of the other lectures I'll review this. Although, since you all took genetics and Bio 1, you should be familiar with the term homozygote and heterozygote. But if you're not, now's a very useful time to review this. Another thing that we'll look at is change in traits over time. So these are different generations of crosses of maize or corn. And this is the percentage of oil in different lines. And in a classic experiment, maize breeders or corn breeders selected for higher oil content or lower oil content. And over at about 50 generations, they decided to reverse their selection to see if they could go back to the percentage of oil that they started with. Remember, these are percents, so they sum to 100. And it's simply impossible for kernels of oil to have no oil. Some is required for the membrane. And they can't be completely oil because there has to be starch and other things and protein for a seed to be viable. This graph is a particularly impressive demonstration of the capacity for selection to change phenotypic traits. In general, different phenotypic traits, such as morphological traits, physiological traits, behavioral traits, and life history traits, vary in how heritable they are. Heritability is a concept we'll come back to later, but it's an indication of how much similarity there is between parents and offspring. For traits that are caused by multiple genes, like all of these classes of traits, where it's usually not a single gene or a single locus with a few alleles, but many genes with many loci that determine them, we see differences in heritability of these traits. So another thing we'll look at, and I've left this figure in here for this, are likelihood ratios. This is something we're going to come back to at the end of the semester. This dotted line indicates a likelihood ratio that's significant after controlling for the number of individual tests being done in a population. And this graph is along positions, centimorgans, in the chromosomes of fruit flies. This kind of graph is one that is quite popular in the contemporary literature. And finally, we may look at more complicated graphs like this. This is a regression slope that's been fitted through observed data to best fit the trend in the data. We see that men and women have slightly different values through this, but that this regression line captures sort of a central tendency in this height data. And I'm going to stop this brief background here, although I aim to provide more materials to some of you who may be the most rusty on algebra.